Ya Kak, lek mulai
Assalamualaikum warahmatullahi wabarakatuh.
Good morning, ladies and gentlemen.
Selamat pagi dan salam sejahtera untuk kita semua.
The Excellencies, Rector of University of Jember, Dr. Insinyur Iwan Taruna M.Eng.
Yang terhormat, Rektor Universitas Jember, Bapak Dr. Insinyur Iwan Taruna M.Eng.
The Honorable First Vice Rector, Dr. Andes Zulfikar, PhD. Second Vice Rector, Dr. Andes Wahyu Subhan, MS, PhD. Third Vice Rector, Profesor Dr. M. Sultan, MPD.
Yang kami hormati, Wakil Rektor 1, Dr. Andes Zulfikar, PhD. Wakil Rektor 2, Dr. Andes Wahyu Subhan, MS, PhD. Dan Wakil Rektor 3, Profesor Dr. M. Sultan, MPD.
The Honorable all of the Dean in the University of Jember.
Yang kami hormati, Dekan di lingkungan Universitas Jember.
The Honorable Chairman of ICCGANT Research Group, Profesor Dr. Andes Davik, MSc, PhD.
Yang kami hormati, Ketua ICCGANT Research Group, Profesor Dr. Andes Davik, MSc, PhD.
The Honorable Chairman of 4th ICCGANT 2020, Profesor Dr. Andes Suratno, MSI.
Yang kami hormati, Ketua Panitia ICCGANT 2020, Profesor Dr. Andes Suratno, MSI.
All of our invited speaker, Profesor Dr. Basuki Widodo, MSc, from 10 November Institute of Technology Indonesia, Dr. M. Katachalam from Fongunadu Arts and Science College, India, Professor Adil Baghirov, PhD, from Federation University, Australia, Dr. Joe Ryan from School of Electrical Engineering and Computing, Australia, Professor Dr. Andes Lamin, MCom, SC, PhD, from University of Jember, Indonesia.
Yang kami hormati, invited speaker, Profesor Dr. Basuki Widodo, MSc, dari Institut Teknologi 10 November Indonesia. Yang kami hormati, Dr. M. Katachalam dari Kogunadu Arts and Science College, India. Profesor Adil Baghirov, PhD, dari Federation University, Australia. Dr. Joe Ryan dari School of Electrical Engineering and Computing, Australia. Profesor Dr. Andes Lamin, MCom, SC, PhD, dari Universitas Jember, Indonesia.
And of course, we would like to welcome all of our guests and participants for today's agenda.
Serta hadirin yang berbahagia.
First of all, let us express our gratitude to God for the blessing and the guidance given to all of us so we can come and join this event without any obstacles.
Marilah bersama-sama kita panjatkan puji syukur kehadirat Tuhan Yang Maha Esa, karena atas limpahan rahmat-Nya kita dapat menghadiri acara
The Fourth International Conference Combinatorics, Graph Theory and Network Topology, ICCGANT 2020. Ladies and gentlemen, the following agenda for today's conference are: first, opening; second, singing Indonesia National Anthem, Indonesia Raya and Hymne UNEJ; third, prayer; fourth, speech from Chairman of 4th ICCGANT 2020, speech from Chairman of CGANT Research Group and official opening; seventh, photo session, and the last is closing.
Hadirin yang berbahagia, berikut adalah susunan acara pada pagi hari ini. Acara yang pertama adalah pembukaan, dilanjutkan dengan menyanyikan lagu Indonesia Raya dan Himne Universitas Jember, kemudian dilanjutkan dengan pembacaan doa, sambutan Ketua Panitia ICCGANT 2020, sambutan Ketua SIGANT Research Group sekaligus membuka acara, dilanjutkan dengan foto bersama, dan diakhiri dengan penutup.
Ladies and gentlemen, the following agenda is singing Indonesia National Anthem, Indonesia Raya and Hymne UNEJ.
Acara selanjutnya adalah menyanyikan lagu Indonesia Raya dan Himne Universitas Jember. Kepada yang bertugas, disilakan. Hadirin dipersilakan duduk kembali.
Ladies and gentlemen, the next agenda is prayer that will be led by Dr. Hobby, SPD, MPD.
Acara selanjutnya adalah pembacaan doa oleh Dr. Hobri SPD MPD. Yang terhormat Bapak Dr. Hobri SPD MPD disilahkan.
Assalamualaikum warahmatullahi wabarakatuh. A'udzu billahi minasyaitonir rajim. Bismillahirrahmanirrahim. Alhamdulillahi rabbil alamin. Hamdasy syakirin hamdan na'imin. Hamdan yuafi ni'amahu yukafi mazidah. Ya Rabbana lakal hamdu kama yanbaghi jalalika wa azim sultanik. Allahumma salli wa sallim wa barik ala sayyidina wa syafi'ina wa dhuhrina wa maulana Muhammad. Allahumma inna nas'aluka salamatan fid din wa afiyatan fil jasad wa ziyadatan fil ilm wa barakatan fil rizq wa taubatan qablal maut wa rahmatan indal maut wa maghfiratan ba'dal maut. Allahumma hawwin alaina fi sakaratil maut wan najata minan nar wal afwa indal hisab. Loving and gracious Allah subhanahu wa ta'ala, you are indeed the giver of all good gifts, and we thank you today for all your blessing. Come fill our lives with your love. Fill our conversation with your grace and truth. Fill this conference, the 4th International Conference on Combinatorics, Graph Theory and Network Topology, ICCGANT 2020, with your presence. Allahumma ya Allah ya Rahman ya Rahim, salimna wal muslimin. Allahumma inna nas'aluka ilman nafi'ah wa rizqan wasi'ah wa shifa' min kulli da'in wa sakamin birahmatika ya arhamar rahimin. We ask that you bless us abundant, and we continue to seek your wisdom, guidance, courage, and strength. Be with us in our deliberation, and have us to be wise in the decision we make for the good of all those who have placed their trust and confidence in our conference. Ya Allah, Ya Aziz, Ya Ghaffar, Ya Rabbal Alamin, give us insight to lead integrity, that our hard work may reflect what is right and good. Keep us from short-sightedness and pettiness. Help us to make contribution to science that are for the good of all, and guide us blind self-interest. Dear Allah, grant us the humility to always seek your will in all that we do and say. All glory to be you, loving Allah subhanahu wa ta'ala, now and always. Amin. Rabbana atina fid dunya hasanah wa fil akhirati hasanatan wa qina adzabannar wa adkhilnal jannata ma'al abrar ya aziz ya ghaffar ya rabbal alamin. Subhana rabbika rabbil izzati amma yasifun wa salamun alal mursalin walhamdulillahi rabbil alamin. Assalamualaikum warahmatullahi wabarakatuh.
Ladies and gentlemen, the next agenda is speech from Chairman of 4th ICCGANT 2020, we would like to invite Profesor Dr. Andes Suratno, MSI.
Acara selanjutnya adalah sambutan oleh Ketua Panitia ICCGANT 2020. Kepada yang terhormat Profesor Dr. Andes Suratno, MSI, disilahkan.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Alhamdulillahirrabbilalamin. Wassalatu wassalamu ala asrafil anbiya'i wal mursalin Sayyidina Muhammadin wa ala alihi wa sahbihi ajma'in. Allahumma sholli ala Muhammad wa ala ali Sayyidina wa maulana Muhammad. Honorable Rector University of Jember, Honorable Dean of Teacher Training and Education Faculty, University of Jember, Honorable Dean and Vice Dean of the University of Jember, Honorable Chairman of ICCGANT Research Group, University of Jember, all distinguished invite speaker and participants. First of all, on behalf of the organizing committee, I am delighted to welcome you to the International Conference on Combinatorics, Graph Theory, and Network Topology, ICCGANT, in the year 2020. I am pleased to see all of you in this forum. About 150 participants have joined this conference. The conference is held to welcome participants from around the world with broad and diverse research interests of mathematics, especially combinatorics, mathematics, natural science, and their application as well as education. I am also pleased to note the majority of our participants come from various universities, both within and beyond Indonesia. I would like to address my special now to our keynote speakers, Dr. Joe Ryan, Professor Basuki Widodo, Profesor Martin Baca, Dr. Katachalam, Professor Slamin, and Professor Baghirov, and then Professor David. This is the fourth international conference on combinatorics, graph theory, and network topology, supported by ICCGANT and INACOM. The mission of this annual agenda is to become an annual international forum where civil society, organization, and representative research student, academic and researcher, scholar, scientists, teacher, and participant from all over the world could meet in and exchange an idea to share and to discuss theoretical and practical knowledge about mathematics in application. Furthermore, I would like to express my sincere appreciation to the first one, the Rector of University of Jember, Bapak Dr. Iwan Taruna, Magister Engineering, and the second Chairman of ICCGANT Research Group, and also Dean of the Teacher Training and Education Faculty, the University of Jember, Professor David, who have shown their profound support in making this conference available. I believe that you will have an exciting meeting here in Jember University. Please use this opportunity and interact with each other to exchange your experience and ideas for the future. Finally, I wish all the success to the conference participants, and let me once again extend my warm welcome and regards to all participants. I wish you an inspiring and enjoyable conference. Assalamualaikum warahmatullahi wabarakatuh.
Ladies and gentlemen, the following agenda is speech from the chairman of ICCGANT Research Group, and also to officially open today's agenda, we would like to invite Profesor Dr. Davik, MSc, PhD.
Acara selanjutnya adalah sambutan oleh Ketua ICCGANT Research Group sekaligus membuka acara pada pagi hari ini. Kepada yang terhormat, Profesor Dr. Davik, MSc, PhD, disilahkan.
Assalamualaikum warahmatullahi wabarakatuh. Selamat pagi dan salam sejahtera untuk kita semua. Om Swastiastu, Namo Buddhaya, salam kebajikan. Good morning everybody, either in the cloud meeting room and in this building. Alhamdulillahi Rabbil Alamin. Assalatu wassalamu ala asrafil anbiya wal mursalin Sayyidina Muhammadi wa ala alihi wa sahbihi ajma'in, amma ba'du. The Honorable Rector of the University of Jember, Bapak Dr. Iwan Taruna, M.Ing, the Honorable all the invited speaker who are joining the 4th International Conference on Combinatorics, Graph Theory and Network Topology. I believe they already joined with our cloud meeting room. They are Professor Adil Baghirov from the University of Manchester, of Ballarat. I say it again, Professor Adil Baghirov from the Federation University of Australia. It was Ballarat University. And then Associate Professor Dr. Joe Ryan from the University of Newcastle. Associate Professor Dr. Katachalam from Kongungadu Art College, India, and the rest are from Indonesia. They are from ITS, Professor Dr. Basuki Widodo, MSc, and then Professor Dr. Slamin, MCom SC, PhD, and all the organizing committee, and of course lovely participants who join this conference today. Ladies and gentlemen, due to the COVID-19 outbreak, 2020's conference is held in webinar format. Last year, we invite you to join this conference and sitting together in this room, but government restrict to have a huge number of participants gather in the same room meeting, and finally, I regret to say that we should have in webinar format. But even we are having a meeting online, I believe it will not reduce the effectiveness of idea sharing through this conference. It will not reduce the benefit of having share an idea of the recent result of the research. The aim of the conference, of course, to bring all the participant idea, either participant only or the parallel presenter, such that we know each other, what you are doing, what I am doing, what the other researcher doing. Once we have known each other, and then we can have a benchmarking of the research for the future research life, for the better research life. Of course, better performance in the research. I believe ICCGANT as a research group at the University of Jember persistent and consistently provide this conference for you to have a dissemination of the research. As we know, we have faced some research step from the exploring research, or we can say exploration research. And then the second one, we have innovation research. And the last one, we have diffusion of the research. The presence of the conference is a part of diffusion of the research. The research literacy not only end up by reporting a document to the grants provider, for example. But after you have a result, after you have a writing a research report, the big job later on is how to disseminate to other people in such a way people understand what you have done, what you have gained in the research. I believe this conference is a medium of share an idea, as a medium to open your mindset, as a medium to improve your quality of research, because there are a lot of participants, not only from Indonesia, as well as from all over the world, from India, from Pakistan, I see, as well as from Philippines. I seen here Agnes already joined with us, with her student as well. This conference, I believe, is benefiting a lot to all of you. By reciting Basmalah, I declare this conference is open for all of you. Thank you very much. Wallahu ma'afiq ila aqwamit-thoriq. Wassalamualaikum warahmatullahi wabarakatuh.
Ladies and gentlemen, the next agenda is photo session. We would like to invite all of our guests to the stage, and also for our online guests, we would like to ask you to prepare your camera.
Acara selanjutnya adalah foto bersama. Hadirin dimohon untuk mengambil tempat, dan untuk peserta Zoom meetings dimohon untuk menyalakan kamera dan menghadap kamera masing-masing. Baik, akan kami hitung 1, 2, 3. Sekali lagi, akan kami hitung 1, 2, 3. Baik, oke, sekali lagi. Freestyle. 1, 2, 3. Baik, disampaikan terima kasih. Kami persilakan untuk kembali ke tempat.
Ladies and gentlemen, entering the main agenda for today's event, paper presentation by the invited speakers, we would like to invite our moderator. Please welcome Rizky Febri Andika Hudori, SPD MPD, and Rido Alfarisi, SPD MSI. Before we start our paper presentation, we would like to give you 5-minute breaks to prepare. Thank you.
Mana? Oh, mana? Mana Adil? Mana Adil? Coba tunjukkan. Dia tunjukkan di mana itu. Kok nggak kelihatan saya? Dipin. Adil dipin. Tadi katanya ada. Nanti kadung di depan dia tidak siap, malah khawatir. Oke, Prof. Adil. Good morning,
Yes.
Prof. Adil. Can you unmute your audio?
I did it.
Do you hear me, Prof. Adil?
Yes,
I'm David
yes, I
speaking
can
now.
hear you very well.
Okay. We will start right now. Okay, thank you very much.
Thank you.
Well, okay. Good morning, ladies and gentlemen. I'm pleased to see here as your moderator. I am Rizky Febri. Today, in this first plenary session, we are going to have 3 invited speakers. The first one is Professor Adil Baghirov, PhD, from Federation University, Australia. The second one, Professor Dr. Basuki Widodo, MSc, from Institute Technology, 10 November, Indonesia. The third, Dr. M. Katachalam from Combinatorics Arts and Science College, India. For the rules, please, for all the participants, you can mute during the presentation. And the second one, for all invited speakers, you have an hour, including question and answer session. Well, ladies and gentlemen, for the first speaker is Professor Adil Baghirov, PhD. He is from Department of Mathematics, School of Engineering, Information Technology and Physical Science, Federation University of Australia. His research interests are optimization, non-smooth optimization, global optimization, operation research, data mining, optimization method in machine learning, optimization of water distribution system, and computational intelligence. And today, he will bring a presentation entitled Non-Smooth and Combinatorial Optimization Models in Machine Learning. Well, good morning, Professor Adil Baghirov.
Okay, can I start?
Hello, good morning.
Yeah, good morning.
How are you doing?
Good, everything's fine. Yeah.
All right, thank you. Sir, you have an hour to present your material. It includes a question and answer session.
Yes.
Okay, thank you, sir. Floor is
Okay.
yours.
Okay, thank you very much for your introduction. And first of all, I would like to thank Professor Dafik for inviting me to give this talk in this conference. So I will first try to share my screen with you. And sorry, that's this one. Can you see my screen?
Yes, sir.
Good. Okay. As you said, I will talk about non-smooth and combinatorial optimization models in machine learning. So I'm Federation University Australia, and first of all, I would like to say that we are proud to have such successful graduates like Professor Dafik, who was, in fact, graduated from our university. So today I will talk about different problems in machine learning, and to present different models for solving such problems. That will include three different problems. I'm sorry, that's I think that. Yes, it works this way. So this is outline of my talk. So I will give a very brief introduction. Then I will talk about three different problems where we can give both a combinatorial optimization and also its reformulation as a non-smooth optimization model of the same problem. So in fact, all these problems which we consider here are in some sense are combinatorial optimization problems. But we will see, when we go through this slide. So first problem we consider is so-called cluster analysis problem. Then I will move to supervised data classification problem, then cluster-wise linear regression, and give some concluding remarks. Sorry. That's okay. So data analysis is a process of gathering, modeling, and transforming data with the goal of highlighting useful information, suggesting some conclusions, and supporting decision making. So data analysis is one important part of a decision making process. There are many concepts in this area, and I want to simply give a clear idea what is machine learning. Machine learning is a scientific discipline that is concerned with the design and development of algorithms that allow computers to learn based on data, such as from databases. So machine learning is about designing algorithms, modeling of problems, and the designing algorithm based on those models. So meaning that machine learning is something that is very close to mathematics. But there are some other concepts here. Not to mix them. In fact, there are a huge also overlap between them. So another concept we use here is called data mining. Data mining is a little bit much more general than machine learning. So data mining is the process of extracting hidden patterns from data. So it contains all steps. To gather, transform the data, to pre-process data. But machine learning is more specific. It concerns about algorithms. So here, that's why my talk is about machine learning, because we approach these problems, problems in data analysis from mathematical, we consider them as a mathematical problem, and develop algorithm, design algorithm for their solution. So whatever we are doing, whatever I will talk today is part of machine learning. So optimization is one very powerful tool for solving many data mining problems. Another name for optimization is mathematical programming. And the non-smooth optimization algorithms are increasingly playing a vital role in modeling and solving data mining problems. So non-smooth optimization is is about minimization or maximization of functions which are in general not differentiable at any point, at all points. So meaning is that gradients or derivatives of those functions are discontinuous. So yes, this is quite a difficult class of optimization problems, But on other side of the non-smooth optimization allows us to give very nice models in machine learning to significantly decrease the number of decision variables. And this actually will allow us to solve this machine learning problems in very large data sets, what is we call now in a big data era. This is very important because now we have we deal with huge number of this data, which can be become dynamical, changing from time to time. So in that sense, use of non-smooth optimization techniques allow us to get better models, which I hope that I will demonstrate today. So we are talking about three different type of problems here about classification, clustering, and cluster-wise linear regression problems. And I will I will present each of them separately. So first, we will consider this cluster analysis problems. In cluster analysis, we assume that we have been given a finite set of points, A, in the n-dimensional space. So we have m points in m-dimensional space, and the aim is to group those points so that in each group points from the same group are similar, and the points from different groups are dissimilar to each other. So meaning is that we have to define what is similar and what is dissimilar. So in order to define that one, we use in machine learning, we use some distance functions. Say we use squared this Euclidean norm, or we can use other norms, L1 norm, L infinity norm. L1 norm is also called Manhattan norm or city block norm, or also we can use so-called Chebyshev norm, which is L infinity norm. Okay, I will give a definition of one class of clustering problems. It's called hard unconstrained partition clustering problem. So we have a set of points, A, and as I said, our aim here is divide A into K disjoint subset, AJ, such that each of these subsets are non-empty. They are disjoint, each, pairwise disjoint, and their union will give me as a whole set A. So simply, I will separate, this divide the whole set into some small subsets. And those subsets are, they don't have intersection, and they are non-empty. And of course, their union will give me the whole set A. And I don't, how to say, impose any other constraints on those clusters. So that is a definition of so-called unconstrained partition clustering problem. So as I said, we have to define what is similarity measure, which is very fundamental in cluster analysis. So in order to solve any clustering problem, you have to first define this similarity measure. Of course, there are many different ways to define that one, but if we are talking about mathematical approach, so those measures can be defined using, in particular, using this distance functions. And here I listed three of them, as I mentioned. First one is so-called Manhattan norm, using L1 norm. We in mathematics we call it L1 norm, and another one is squared L2 norm. Here, squared, because this is not a L2 norm itself. In order to make it L2 norm, I have to take a square root. And this one is so-called Chebyshev or maximum norm or L infinity norm, or another name is a Chebyshev norm. So this is all three main similarity measures we use in cluster analysis. Then I have to formulate my objective functions. And here I will show three of them. First one is that we define this function, which in other words we use it. We call it a clustering error, but better to call it clustering function. So here we have this similarity measure, and assuming that we have this distribution, I mean this clusters here. So function is written so that we simply calculate distance between each point and its cluster center, and we find their sum, and then we divide this sum by m, so that we have averaged clustering error. And then I have to regroup, I mean this cluster, so that to minimize this function. So how can I do it? I can change x, or I can also manipulate with clusters. I mean simply some points you can move from one cluster to another one, and so on. So this is a combinatorial model of that clustering problem. Of course, it is not so easy. No one uses this objective function. I mean, of course, we have heuristic algorithms. They are based on this one. But it is not easy to manipulate with subsets, because if you have huge number of points, it is not so easy. That's why we try to reformulate this problem to get some optimization problem which can be solved by using existing algorithms. So second one is model, again clustering model, is called mixed integer programming model. So here we have our objective function. Exactly, I mean this is similar to previous one in the sense of they have the same values, but their representations are completely different. So what we do here, we introduce so-called membership function, which can be either 1 or 0. So meaning is that if i's point belongs to j's cluster, then we will have 1. Otherwise, we will have 0. Then I can formulate this objective function here. You can see that now I have a completely different order of sums, and here I have the whole set of points. I mean, I included all points. So this is, you can see that we have two variables. One is w, which is in fact matrix, and it has m multiplied by k number of variables here. So and also I have cluster centers xj. So meaning is that I have continuous variables and I have binary variables. That's why we call it mixed integer programming model. Mixed integer comes out because that's decision variables are both binary and continuous. But we have integer because this is 0, 1 here. So this is another optimization model. And here, okay, I mean, this, we give here that's what is this membership coefficient. So it is 1 if this point belongs to J's clusters, and 0 otherwise. Then if you have this one, in the case of squared Euclidean norm, there is the xj's are not, they don't, we don't consider them as a variable because they can be calculated explicitly. But if you use other similarity measures, so we should not, we don't have this explicit formula, meaning is that in those cases we have real mixed non-linear integer programming. So now I want to present this non-smooth optimization model. So what we do here, okay, in previous model we had this coefficients. I want to get rid of them here, sorry. This one, because their number first is huge. M is a number of points, and their number in real life applications can be hundreds of thousands or even millions. So meaning is that we have huge number of integer variables here. And another problem is that this is a binary variable, which is not so easy to deal with such variables, and especially when you have a huge number of them. So this is again some combinatorial optimization model in some sense. Okay, so that's why I want to get rid of this one. What we do here, instead of this one, we introduce so-called minimum operation. So simply means that if I take any point, AI, then simply I calculate this distance between this point and all cluster centers, xj. I have a k of them, and you take minimum of them, because this is our rule, how we assign points to clusters, because we calculate distance between points and cluster centers, and cluster centers which gives us least distance, we assign that point to that cluster. So this is what is written here. So, okay, we don't have anymore this binary variable, which is good news for us. But on the other side, we have now minimum operation. Minimum operation, maximum operation in mathematics makes any function, if you have many functions under minimum or maximum, the function becomes non-smooth. So those functions don't have gradients at all points. There are points where function is non-differentiable. That's why this function is non-differentiable, non-smooth function. Of course, there some will give us even more complex non-smooth function. So that's why this objective function itself is non-smooth function, and that's why we call it the non-smooth optimization model of clustering problem. So now you can see that we don't have any integer variable here, and we managed to decrease number of variables significantly. So we have only cluster centers as a variable, decision variables. And those number of decision variables doesn't depend on number of points. In previous model, we had that situation. So in previous model, this number of decision values depended on number of points, which is not good news, because again, usually we deal with a huge number of points in real life applications. So here, that's good news. Another one that we significantly decrease this number of decision variables. And another thing is that we have only continuous variables. Continuous optimization is always much easier than combinatorial optimization. So that's I would say clear. I'm sorry. Okay, then we can introduce other models here, because our function, yes, this is a non-smooth function, but in fact, I mean, we can dig a little bit more and see that this function is not so bad function. And this function can be represented as this difference of two convex functions. You know, convex optimization is easy. I mean, easier than non-convex optimization, much easier than combinatorial optimization. So if we can get this some structure of our problem, we can develop much better algorithms. So here we have this representation, DC representation of our function, objective function, clustering function, and this DC components are given here. So DC function is function which can be represented as a difference of two convex functions. That's the definition of that one. So here we have that situation. So this is why this is good, because you know that Euclidean norm, squared Euclidean norm, is smooth function. So meaning is that in that case, if you use as for similarity measure squared Euclidean norm, then first function becomes smooth function. But second function is non-smooth and quite a complex one. So meaning is that using this structure, we can separate this part, I mean this smooth part from non-smooth part, which is also good, and we can develop better algorithms for it. So when we compare these two models, first of all, we have to compare this number of variables. So in case of squared Euclidean norm, the number of variables is m and k, and m is number of data points. But in non-smooth case, we have only nk. N is number of so-called attributes, features, and the k is a number of clusters. So you can see that how big is difference. If you divide this one by this one, you will have m can be huge, hundreds of thousands, even millions in real life applications. So that means that we can, using this reformulation, we can make our problem more tractable. I mean, that's in the sense that you can design better algorithms based on that reformulation. So second class of problems, which we will consider today, is called data classification or supervised data classification problems. And again, we will have a look at this one. So in clustering, we don't have any prior information about our data. But in the case of supervised data classification, we have prior information in the form that we know that some points belong to some classes. So we can divide this data set into a few classes. I mean, it's already given us in that form. So if we have that one, so what we do in supervised data classification, simply we find some rules or some functions to separate those classes. And then when we have new observations, new measurements, simply we can use those functions or those rules to classify our point to one of these classes. So one example is that we have, say, tests in hospitals, and we have sick people and the people which are not sick with a specific illness. So we have two classes here. So if we have a rule how to separate them, once we do this test in hospital using, say, blood pressure, I don't know, some other tests, I mean, there are many tests here, level of sugar or whatever, then we can say exactly to which class that person belongs. So that gives us, I would say, additional tool for doctor to decide what to do with this person. Okay, so that's one example, but there are many, many examples here. And also, I mean, this is in this airports and so on. They use this security cameras and to, how to say, classify people. Anyway, so mathematically, we consider here, I mean, two sets and try to separate them using some function. Here, of course, we are talking about functions, how to separate them. So we have set A and set B. So A is contains points which belong to class 1, and B contains points which belong to class 2. So our aim is to separate them. So what we know from convex analysis is we can use linear separability. So you can have one line to separate them. Okay, I think that I have picture of this one here. So you have set A and you have set B, and our aim is to find the line, or better to say in n-dimensional space, this is a hyperplane separating these two sets. How to find them? So we know that hyperplane can be given by x and y. X belongs to this is n-dimensional vector. It's called also normal of that hyperplane, and then we have y called intercept. So if we draw that one set should be on one side and another set should be on another side of that hyperplane. So that's a mathematical, how to say, definition of that one. So this function is negative on one side and the positive on another one. Okay, so we have that exactly that situation here. So meaning is that from convex analysis, we get that the convex hull of these two sets, intersection of convex hulls of these two sets, is empty. And now question is how to find x and y. So we formulate this problem using this one. So both these functions are called error functions. So if point is in the wrong side, so point from this say B, I'm sorry, from B goes to that side, so it we call it, it will give us a positive error. So meaning is that our aim is to minimize that error, to make sure that all points are on right sides of those hyperplanes. So that is a mathematical representation of that error. So then we can reformulate that problem as a linear programming problem. Ti and Zj are these errors for given points, for point I and here for point J. And then we have this one. I mean, this is coming simply from that one, that if Ti is 0, then it is on right side of that one. I mean, side A, set A. Similar here we have here for set B. And the both, I mean, errors cannot be negative because this is error. This is either 0 or positive number. If positive, we have to minimize it to change our hyperplane to make sure that these errors are become 0. Okay, so this was when we have linear separability, but unfortunately in a real life application, linear separability doesn't happen. I mean, it's very rare that we have that. That's why we try to get more complex, I mean, separation here. And the second one is called polyhedral separability. Polyhedral set is set which can be represented as a intersection of finite number of half spaces. Half space can be given by one hyperplane. One side is one half space, another one in another half space. So in order to explain this in better way, I have this picture here. So I have set A and I have set B, and this is 3 lines. I mean, each of them give a half spaces here, half space here, and this one gives half space here. And I consider this intersection of these 3 half spaces. And that intersection I use to approximate set A. And the rest of space I give to set B. So that's it's called polyhedral separability, and its mathematical expression is given here. So we have finite number of hyperplanes. Before we had only one in linear separability case. So then I mean we say that each of them should be negative, but for another set, at least one of them should be positive. So that is a generalization of previous conditions. Then we can write our so-called error function, which is given here. Okay, it's becoming more complex than previous one. Problem here is that first one is not so bad. It is a piecewise convex function, but second one becomes now non-convex, meaning is that it is some tooth shape piecewise linear function, and it's not so easy to minimize such functions. So because this becomes a problem, becomes a non-convex global optimization problem, and the global optimization problems are not so easy. Again, it is about combinatorics, okay? Because you have to find right number of hyperplanes. It's another question here. Problem, of course, I mean, will become more complex here. But even polyhedral separability is not enough in some cases to separate two sets. And then we generalize that one to more complex case. I will show you some picture here. I think that I have. Here, say we have 2 sets, and these sets cannot be separated using only polyhedral sets. It is not possible because you cannot draw any linear function which can separate these two sets. So meaning is that we have more complex case here, and the functions are becoming, separating this one becomes non-convex. And that means that we get the error function, which is more complex. I think that I have better picture here. So we have set A, you can see here with yellow one, and another one is blue one, set B. So you can see that there is no any linear separability here. There is no any, if you draw like this polyhedral set, and it will cut part of this B. So it is no polyhedral separability. So you cannot approximate set using only one polyhedral set. So we use this type of piecewise linear function to separate them. And these linear functions have very specific representation, which is max-min of linear functions. So we use these functions to separate two sets, and using that one, we can now formulate, give definition of so-called max-min separability, because now function is max-min of linear functions. That's why we call it max-min separability. As actually, this is generalization of polyhedral separability, which was generalization of linear separability. So this is a most general case. Max-min separability is most general case when you have two sets containing finite number of points. So we have this situation, and in this case, function becomes even more complex. You can see here we have max-min and the max-min here. Both functions here, this is our error function, and both functions here are this non-convex piecewise linear functions. So it may have a huge number of local solutions. Again, we are coming to so-called combinatorial optimization in that sense. But here we use non-smooth optimization because our functions are non-smooth functions, non-smooth piecewise linear functions. Okay, so that was we have to minimize, of course, this one to find this all these lines which we had here. Sorry, in order to find these lines, or better to call hyperplanes. So we have a non-smooth optimization model, and we can solve this problem as non-smooth optimization problem. Okay, we get we can get also DC, this DC formulation of this problem. So another model which can be, we can problem where we can use non-smooth optimization to make to reduce, in fact, again, the number of decision variables is called semi-supervised this data classification. And one example is to use this support vector machines. Support vector machine is a well-known technique. It is quite efficient. It is a powerful method when you don't have a large number of points. So if your data set is not so large, then SVM is a good option here to apply this method to solve data classification problem there. So what is SVM, support vector machine, is that you have two sets again, and you are trying, in the case of linear support vector machine, you find two parallel hyperplanes. One is supporting this one, set A, and another one supporting set A. And you try to maximize difference between these two, this is distance between these two hyperplanes. And once you found them, if these two sets are linearly separable, simply you draw a line which it goes in the middle here. Easy to calculate that one because you know already this hyperplanes. In fact, these two hyperplanes are parallel to each other, meaning is that they have the same normal vectors. So you don't consider two hyperplanes. In fact, you consider only one hyperplane here. But the aim is to maximize this distance between them. It's called margin. It's called. So we maximize margin. So in fact, then we reformulate it as a minimization problem. So that's not. So transductive support vector machine is about semi-supervised. So semi-supervised means that we know label class label for each data, but we also may have unlabeled points. We call in some cases we call them test points. So if we have that information, additional information, we can use in our data classification problem. But since we don't have their label, we cannot say to which class they belong. So aim here is simply to make sure that those test points are not in between these two lines. So we have to draw these two lines so that not to have any point in between or minimize the number of such points. So it brings us to so-called transductive support vector machines. And a model for that one is, so first one is for SVM, but this one is coming from unlabeled data. And this unlabeled data is given as a penalty, margin penalty function, which is non-smooth because of absolute value here. Of course, I mean, we put all this stuff here because function becomes a non-convex piecewise linear function. So it adds non-convexity and the non-smoothness to our problem, but this is more, this approach allows us to use as much information as possible, which is better than if you use only labeled data. Okay, but it brings us to a non-smooth optimization problem. So then we can minimize this function and to find those hyperplanes. Of course, SVM is not only finding hyperplanes in primal space, it also can be used to use kernels to transform our data to feature space, and then we can get the so-called non-linear function separating classes. And one of them is so-called RBF, radial basis function, which is coming from this normal distribution. Okay, so next our problem, which we will consider, is called cluster-wise regression. Of course, we will talk about cluster-wise linear regression. So I hope that you know what is regression. Regression is about this approximating a regression function, which we don't know. I mean, we do some measurements. We don't know exactly what is regression functions there. Then we consider different class of functions to approximate that regression function. And say multiple linear regression is about approximating those data using linear functions. So cluster-wise linear regression simply considers more than one linear function. Because in multiple linear regression, we consider only one function, one linear function, but here we consider several linear functions to approximate our data. So it brings us to this type of problem. So you have this data. So that is what we have here. We call it input. And what we have on y-axis is, we call it output. So aim here is to find this relationship between input and the output. This is the aim of this regression. But here again, I want to say that we use more than one linear function. So you can see that we have two linear functions here, and they actually take some points around them and here. So why actually we do this one? There are many applications, especially in finance. I mean, because you know what's happening in share market. Something happening one day and everything drops and again starts to increase. Whatever we have, I think that this year is one good example of that one with COVID-19. I mean, all this dropped, at least in Australian share market. This happened. I think that similar happened in United States also. Maybe similar in Indonesia, I don't know exactly, but this is one good example. When we have different functions, we have to have used more than one linear function to approximate our data, similar to that one. So here we have now 4. You can see that we get completely different approximation. And in this data, we have again two linear or straight linear functions. So what is our point here? We have lines, call it hyperplanes, linear functions, and points are, this is gathered around them. So this means that now we have, again, clusters, because clusters are together. I mean, this is similar points. But in clustering, we used only one point, the cluster center. Here we use, instead of point, we use linear functions to find those clusters. So shape of clusters is completely different from shape of clusters in clustering problems. So here we have a combination of two important techniques in machine learning. One is clustering and another one is regression. Okay, so meaning is that when we give a definition of a cluster-wise linear regression problem, again, we will give a similar problem, a similar definition which we had in clustering. So again, our aim is to divide our set into given K clusters, and for each cluster to find their regression coefficient. This is completely different. And another one is that here we have a prior information about our data. We have output. We don't have that in clustering. So this cluster-wise linear regression or cluster-wise regression is the combination of two techniques, clustering and regression. And the definition is given here in this one. Then what we do, we define this regression error. Then we can define our function. This is a regression error function for cluster-wise linear regression problem. You can see that quite similar to what we had in the case of clustering, but now here, instead of similarity function, which we had there, this was distance functions, we have regression error for each linear function. So different, in fact, but structure the same. So meaning that we can do similar stuff there. So in many cases, we can consider P equals to 1. This is L1 norm. So in regressions, they call it L1 risk. Or we can take P equals 2. It calls also L2 risk function. So otherwise, I mean, this will give us this non-smooth optimization model. This function, again, is nice function. It can be represented as a DC function. DC representation helps us to design better algorithms. And so we have non-smooth DC optimization model and other models. So, okay, here we consider it three different problems coming from this machine learning. In fact, from data mining. Okay, machine learning is about designing algorithms, so better maybe to call it data mining. So here you can see that we can use a different approach to to model these problems. Main difference between those models in their complexity. So when we use combinatorial optimization models, we get huge number of variables, which are in fact, in some of them are integer variables, and everyone knows that integer programming is very tough, I mean, the class of problems in optimization. Non-smooth optimization is also not so easy, but what the non-smooth optimization gave us in all three cases, we decreased the number of decision variables significantly. Okay. Moreover, those non-smooth optimization models allowed us to explore structure of those problems, and using that structure, we can design even better algorithms. Instead of using, say, general purpose algorithms, we can develop algorithms which are specifically for this type of problems. So that's, I mean, you can see that we have different problems, but models are, in some sense, they are quite similar to each other, especially when we are talking about cluster-wise linear regression and we are talking about clustering. Problems are, from optimization point of view, not big problem, not big difference between them. Of course, they address completely different problems. Okay, so also that's I added here list of references, which if someone interested can have a look. And these papers present those results which actually I discussed here. So thank you very much for your attention, and I stop here.
Well, okay, thanks a lot, Professor Adil Baghirov. It is a very super presentation. Well, ladies and gentlemen, we have still 15 minutes, so it's time for you to deliver questions. Perhaps I will take one or two participants to deliver the question. Maybe you may type in the chat box, or you may raise your hand. It indicates that you want to deliver the questions. Please. Well, so we are still waiting for the questions for Professor Adil Baghirov. Ladies and gentlemen, please, you may type your questions into chat box, or you may raise your hand. That indicates you want to ask something dealing with his title. Well, okay, so I'll give you for the last time, ladies and gentlemen. If you want to have a questions dealing with Professor Adil Baghirov's presentation, you may type into the chat box, or you may raise your hand. Well, okay. Hello, Professor Adil Baghirov. Are you
Yes.
still there? Yeah, perhaps all the participants have already understood about your presentation.
That's good.
Thanks a lot for your joining in this conference. And before we go to the second invited speaker, let me read for the short summary from the presentation of Professor Adil Baghirov. Problems in everyday life can be modeled into mathematical models. Every mathematical model requires a solution. There are many methods in solving mathematical models, namely unsupervised learning, supervised learning, regression analysis, and cluster-wise regression analysis methods. These techniques have many applications in different areas of human activity. We discussed non-smooth optimization reformulations of these problems, and we have designed of more efficient and accurate algorithm for solving mathematical models. Well, thanks a lot for Professor Adil Baghirov. Ladies and gentlemen, give a virtual big applause for Professor Adil Baghirov.
Thank you very much.
Thanks a lot, sir.
Thank you.
Well, ladies and gentlemen, so we will go to the second invited speaker. Let me call Professor Dr. Basuki Widodo, MSc. Hello, Professor Dr. Basuki Widodo. Are you there?
Yes.
Can you...
Good morning. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam
All of you.
warahmatullahi wabarakatuh. I'm good, sir. Thank you. Well, ladies and gentlemen, before we begin, for the second invited speaker, let me tell you for very short introduction Professor Dr. Basuki Widodo MSc, he is right now the president of Indonesian Mathematical Society. His specializations are computational fluid dynamics, mathematical modeling, numeric method, numerical simulation, and applied mathematics. He has got his professor of Mathematical Modeling and Computer Simulation from Ministry of Education, Republic of Indonesia in 2010. And today, he will bring a presentation entitled Magnetohydrodynamics Fluid Flow Passing Through a Sliced Magnetic Sphere Influenced by Mixed Convection. Well, good morning, Professor Dr. Basuki Widodo.
Good morning.
Are you ready for giving your presentation?
Yes, I have ready now.
Okay, all right. Ladies and gentlemen, please welcome Professor Dr. Basuki Widodo. Floor is yours.
Thank you very much, moderator. Okay, Assalamualaikum warahmatullahi wabarakatuh. Bismillahirrahmanirrahim. Alhamdulillahirabbil alamin. Wassalatu wassalam ala israfil anbiya wal mursalin. Sayyidina wa maulana Muhammad wa ala alihi wa sahbihi ajma'in, amma ba'd. The Honorable Rector of State University of Jember, Dr. Insinyur Iwan Taruna MN, Professor Adil Baghirov, and the others distinguished keynote speaker, the invited speakers, the participants, and the committee of the International Conference on Combinatorics, Graph Theory, and Network Topology, Stanford by ICCGANT 2020. Praise the presence of Allah God Almighty, who has bestowed the grace, favors, and gift so that we can share information today in a healthy and full of happiness. Our greetings and prayers go out to the great Lord of our Prophet Muhammad. Okay. In this opportunity, we would like to convey our highly appreciations to Professor Davik and the committee of the International Conference on Combinatorics and Graph Theory and Network Topology that have invited me to join our Prophet to join of this conference. Sorry. Slightly different from what has been presented by previous speaker for this conference. I am happy to deliver a part of my research concerning with the problem of magnetohydrodynamics, viscous fluid flow passing some object. Let me show you the our presentations using PowerPoint. Okay. Sorry. You can. Okay. Yes. Can you see our presentation now?
Yes, sir.
Okay. Thank you very much. Right. Slightly different from what has been presented by previous speaker. Yeah. For this conference, I am happy to deliver a part of my research concerning with the problem of magnetohydroviscous fluid flow passing some object. This topic currently getting quite a lot of attentions in relation to the energy actually, particularly in renewable energy and new energy. We therefore consider mathematical modeling on magnetic hydrodynamic viscous fluid flow past a magnetic slide sphere when the effect of mixed convection included. When right, the magnetic hydrodynamic flow consider about the fluid flow that can conduct electric currents and influenced by magnetic fields. So that's why the magnetic hydrodynamic flow is the study of interactions between electromagnetic phenomena and induction of the fluid. The development of fluid mechanics is growing rapidly now, along with its benefits and uses in the various industrial fields and engineering, such as magnetohydrodynamic generator, and accelerator, also nuclear reactor coolant, yeah, and crystal growth. Besides that, the study of magnetohydrodynamic also can change characteristics of the velocity and temperature of the fluid. This is used in various technical fields such as ship propulsion engines. A fluid flow that is controlled using magnetic field and fluid temperature has been investigated for a long time. But the technology and computing at that time were still inadequate. Electrical current from a fluid flow can be produced by making changes in velocity and temperature. Recently, there have been many studies on magnetohydrodynamic in various geometric shapes, yeah. Fluid types, yeah, cylinder, flat plates, and sphere, and fluid types, viscous fluid, nanofluid, micropolar fluids, and the conditions that influence them. For instance, natural force and mix, combination of natural and force. Like the research conducted previous research, for instance, by Wijaya, Nur Salim, Ningtyas, and Martianto, that discussed the fluid in a magnetohydrodynamic flow past sphere. Here we have these researchers. For our presence here, we discuss about the kind of fluid viscous with the object is a sphere, which is a slice with the angle with certain angles, and then consists of magnetics and also affected by mixed convections. And we solve this problem using numerical solutions, numerical technique, using Keller box methods, that is implicit kind of technique in numerical. And we here consider about the magnetic hydrodynamic viscous with past a slice sphere under the effect of mixed convections, and the geometry of the object used in this research is a magnetic and then slice using particular angle we call a theta. Yeah, when we use theta, for instance, 30 degrees, so the angle is from this axis up to here for the 30 degree, and this one for the 30 degree. So when we put it the straight line, so we have the slice of the magnetic, so the slice of a sphere. And this object consists of magnetic. So we, I mean, the fluid flows from bottom to the top here. Yeah, this is streamlined, and here we call lower stagnation point. So the fluid can flow past of this slice magnetic sphere, and therefore we introduce some coordinate systems here. So this is the locations of fluid, for instance here. Yeah, the reference points are the point of zero. We put it in the central of the sphere. So we can denote the locations of the positions of the fluids. For instance, of here, so this is X and Y. X is a measure from here to these points, and Y measure from the central to the point here. So when we put it, or when we take X equals 0, it's meant that the positions in front of the lower stagnation points. So this is our considerations for this research. So this is the physical model, and this is the coordinate systems. Now from these problems, so we developed a mathematical model or mathematical formulations that these formulations can be developed from continuity equations, momentum equations, and energy equations. So when we analyze, now we have here, this is the equations or the formulations when we use units or when we use dimensions. So we call dimensional equations. So we have three equations, yeah, because we interested in 2 dimensions, so we cut or we truncate the equations becomes 2 dimensions form. So we have for the continuations, you can see in the equations of 1 and momentum equations in X and Y directions, in equation of 2 and 3 respectively. And for the energy equations, we have in 4 equations or formulations. Following with the boundary conditions as follows, yeah. It's meant that for any positions, I mean when temperature is denoted by T infinity, it's meant that temperature far away from the from the object. So we have velocity component in x directions and y directions is zero respectively. But for the speeds on the far from the sphere, so we can find or we can obtain using numerical solutions. And here is an addition information that for the speeds and for the temperature, for the speeds, even in x directions and y directions, when on the boundary, on the surface of the boundary of the sphere is a zero, and the temperature is denoted by TW. It's mean temperature on the wall, yeah, for the y equal to zero. It's mean that this is zero. It's mean on the boundary, on the surface of the boundary of the sphere. So this is the notations of these equations. Rho, it's mean fluid density, mu is a fluid viscosity, and G is a gravity, and so on. Now, for solving these equations, for solving those equations, so we need to transform the dimensional equations with the non-dimensional equations. Because what? Because we don't need units or dimension. So we just put on some value, and then we can obtain the solutions. So that's why for this sections, we show you how to make these equations, non-dimensional equation, it means by into non-dimensional equation using or introducing non-dimensional variables, namely x equal to the ratio of x bar over a, and y is a square root of Reynolds number multiplied by y dash over a. A is the radius of the object of the sphere, and b equal to b b star ratio of b over a, and so on. And also, we use some parameters, non-dimensionless parameters, like m is a magnetic parameters, alpha is a convection parameters, alpha is a ratio of Grashof number, and square of Reynolds number. What is a Grashof number? Is that one is the ratio of temperature, diffusion temperature, and viscosity on the boundary, on the surface of the sphere, and also Prandtl number. Here, now when we substitute this variable into previous dimensional equations, so we obtain non-dimensional equations like this: continuous equations, multiple equations, and energy equations here. So now the equations now is a transform completely. Yeah, becomes this formulations because in this problems or in this research, we just need to see what happens, the characteristic and the property closely or nearly the surface of the boundary of the surface of the sphere. So we use approximations. Here we use a boundary layer approximation. So now the Reynolds number, when we imply to the previous non-dimension equations, now we obtain we obtain the formation look like this one. Here, the momentum equations in y-axis disappear or vanish because this Reynolds numbers, right? And because we consider in a two-dimensional flow, so we allow to use string functions, right? And then from this functions, from the string functions, now we can define the speed in x-axis, and the y-axis looks like this formula. When we substitute in the previous equations, like the one here, so the continuous equations is purely satisfied. So we can finish the continuous equations. So now we have just two equations, namely momentum equation in x directions and energy equations. Now, because in this discussions, we are allowed to use string functions. So in this discussions, we can use similarity equations. So for the string function can be denoted by these formulations when t is this expressions and eta is these expressions. So when we substitute these equations into the previous of the string functions equations, so now we have here for the small time, this is for the time is very small, and for the other hand, for the last time, we have two equations. So for this moment, we interested in the lower satisfaction point. It means that x equal to 0. So when we put it here for x equal to 0, so now we have here for the small time case, yeah, with the boundary condition here, and also for the last time case, we have this formulations with the boundary condition here. So when we solve numerically, so we have to introduce the methods for this research. We solve numerically using color box method. That is for the we have in the color box we have 4 steps technique. For the first step is to reduce this previous equations here become first order equations. following by discretizations, and then making linearized. Now we can solve these equations. For this solutions, a numerical solution is mean we use computer programming using MATLAB, yeah, using MATLAB, and then we obtain some results because we continue the calculations. So first of all, we need to compare uh, our solutions with the results that have been produced by Martianto. So we take comparisons. It's been this is for validations of our numerical solutions. Because of what? Because we need to know that what I have done is valid for the calculations in the next calculations, in the next numerical solutions. Yeah. This is here because our research exactly, I mean, because the result what we have obtained were exactly the same as those produced by Martianto. So that these results add to our confidence to carry out further numerical solutions, numerical calculations. Because of that, in the next time, we variate the values of parameters such as Prandtl number, magnetic parameters, /Angel parameter, and mixed convection parameter to analyze the velocity and the temperature in front of the lower stagnation point. So now, when we take the variation of magnetic parameter for the Prandtl number of 0.7 and convections parameter equal to 1, and the /Angel of magnetic sphere is 30 degree. So when we put it, the M varies, yeah, from 1.3 up to 2.3. So what is this number? This is number is mean that this is a magnetic parameters from iron, cobalt, steel, and zinc. So when we put it rho density and shear stress of the sphere, I mean the object. So we have this result. This is for the velocity, and this figure is for the temperature. You can see here, when we increase the number of magnetic parameter, so we have or we obtain the velocity profile becomes decrease, as well as the temperature. So we can see here. You can see here. So this is because the fluid that is far from the position of the surface, yeah, has slight influence on Lorentz force. Okay. Now we change these parameters, yeah, but here is similar. So what is the result? See here, yeah, when we change alpha, now it becomes 2, Prandtl number becomes 1, and theta S is a 45 degree. So we have the similar results of previous result, numerical results. So this is to make confidence that this is because the fluid fall from the position of the surface. So the sphere has a slightly influence on the Lorentz force. Now we change the variations of parameters. Now we change the convection of parameters, yeah, using the same previous of the parameters before. So now we have, when we increase the value of convection parameters, see here. So now the profile of temperature becomes increased. See, and from the for the temperature profiles become decreases. So what is happens? This happens because the external energy in the fluid flow caused by external force given, and this happens because there is no repulsive force that arises in the fluid flow. Now we can move it to another results when we when we change these parameters, but here is similar, yeah. So we have still similar with our previous results. So this means that this is because of external energy on the fluid caused by external force given, no repulsive force arise in the fluid flow. Now we change of variation of Prandtl numbers. Yeah, 0.7 is for gas. Prandtl number 1 is for salt water, and for 7 is a water, purely water, and 100 is for oil. When the value of the magnetic parameters and convection parameter 1 and theta is 30 degree. So we have these results when we increase the Prandtl number. So the profile of the velocity become decreases, and also for the temperature become decreases. Okay, but now when we change for other parameters, so we have similar results. Yeah, similar results like previous results. Now we variate the slice of magnetic fields. So when we use slicing angle of in the surface, yeah, of 15 degree, 30 degree, 45 degree, 60 degree, 65 degree, 70, and up. This is close to the horizontal of the surface in front of the fluid is 85. So we have here, when we increase the slice, so the velocity profile becomes increased. However, for the temperature of the fluid becomes decreased. So What is the problem here? This is because the surface of slash sphere gets wider, okay, and resulting in a decrease in friction between the fluid and the surface, so that the velocity increase. This happens also because the greater of theta s can cause the surface to be wider, which is impact in the distribution of heat of sphere faster than the distribution of heat of the fluid. So that the temperature decreases. Okay. Now, when we move to other results, when we change, these parameters, but here still similar. So we have here similar, So the conclusions, the numerical solutions on the problem of magnetohydrodynamic fluid flow on the lower stagnation point in a viscous fluid pass slice sphere when mixed convection included was already studied. We conclude that when magnetic parameter increases, then the fluid velocity decreases and the fluid temperature increases. For the convection parameter increases, then the velocity of the fluid increases. However, the temperature of the fluid decreases. For the Prandtl number parameter increases, then both of velocity and temperature of the fluid decrease. For the slash angle parameter increases, then the fluid velocity increases, but the fluid temperature decreases. For this moment, we thank to LPPM for giving us funding for this paper. This is our references, and thank you. Thank you very much.
Thanks a lot, Prof. Basuki. Well, okay, for the participants, you may deliver the questions because this is the session of question and answer. You may type your question in chat box, or you may raise your hand, or you may unmute directly your microphone and then you can ask directly to Professor Basuki. Please, ladies and gentlemen. Well, okay, ladies and gentlemen, now times for questions and answer. So you may ask directly to Professor Basuki dealing with his presentation about magnetohydrodynamics. You can unmute your microphone and then you can ask directly to Professor Basuki. Or maybe if you are shy to unmute your microphone, you may type your questions through chat box. Okay, so we are still waiting for the participants who want to ask the questions to Professor Basuki. You may directly unmute your microphone and then you may speak. You may deliver questions to Professor Basuki, or you may type your questions through the chat box. How's that? No one?
Okay,
yes, please. There is a participant
yes.
named Hasna. Okay, yes,
Thank
sir.
you,
Okay.
Mr. I want to ask Prof. Basuki Widodo. He's
Yes,
my supervisor in my master in ITS Surabaya.
yes, please.
Okay, Prof. Good morning.
Good morning. Are you
Okay,
fine today?
I'm very interested in your research until now. I want to ask about how to get Prandtl number, Prof.
Yes.
We want to know Prandtl number. It means why just 1 up to 100? Maybe any boundary from maybe 1 up to 100. Maybe any other number. Why 1 is the water, 100 is oil. Maybe can more explain about Prandtl number. Okay, thanks.
Okay. Thank you very much for your questions. From this value of the Prandtl number, I obtained from the book, the book Fluid Mechanics, that for the fluid, for the gas, for instance, we have obtained the number of Prandtl number is 0.7. For the salt water, we have obtained number of 1 and 7 for water and 100 for oil. This is because we use for this research as a viscous fluid flow. We can put it, or we can take this number and then put it in a numerical computations. Otherwise, we can use any numbers, but no meaning. I mean, for instance, 0.3. What is the fluid? So we can tell. We cannot tell. We cannot tell what is the Prandtl number when we use when we take 0.3. That's why we use this Prandtl number that well known in handbooks of fluid mechanics. And what is Prandtl number? The Prandtl number is the ratio of temperature on the fluids. Diffusivity. That one is a diffusivity of temperature in the fluids, and the temperature, closely or on or nearly on the surface of the object, of the sphere. That one. What is it? Pak
Muhammad Afrikan, sir.
Muhammad Afrikan.
Okay.
Muhammad Afrikan. Sorry about that. I forgot. Yes. Is it clear what I have mentioned before?
Yes,
Yeah.
understand and clear.
Yeah. And I am happy if you want to join me again for this research, because this research impact on the technology is highly impact. We welcome if you want to join with our team in this research. Thank you very much.
Okay. Thank you. Thank you. Yeah, welcome.
Well, okay. Thanks a lot for Mr. Tafrikan for delivering your questions. For the other participants, please, we have still time to question and answer session. So you may deliver questions directly to Professor Basuki, or you may type your question through chat box. Okay, so you may unmute your microphone and then you can ask directly to Professor Basuki. No one? Well, okay. Hello, Professor Basuki. Are you still
Yes.
there? Yes, Prof. Perhaps most of the participants have understood your material. Thank you very much for joining our
Thank you very
conference.
much. Yeah.
Before we end the second invited speaker, let me tell you about the short summary. We consider mathematical modeling of magnetohydrodynamics, viscous fluid flow when passing a magnetic slide sphere, in which the effect of mixed convection included. Therefore, developing dimensional governing equation from the law of the mass conservation, momentum conservation, and energy equation, we obtain that when magnetic parameter increases, then fluid velocity decreases, but fluid temperature increases. For the mixed convection parameter increases, then the velocity of the fluid velocity increases, but the temperature of the fluid decreases. Well, that's all for the second invited speaker. Before we go to the third speaker, give virtual big applause for Professor Dr. Basuki Widodo.
Thank you very much. Wabillahi taufiq wal hidayah. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thanks a lot, Professor Basuki. Well, ladies and gentlemen, we have still one, the last but not the least. So I'll call Mr. Dr. M. Katachalam. Are you there, Mr. Katachalam?
Yes.
Yes, hello, good morning.
Good morning.
Okay, how are you?
Fine.
Great, so nice to meet you again. It is my second time to accompany you in this conference.
Yeah.
Okay, well, ladies and gentlemen, before we go to the third invited speaker, let me tell you a very short introduction about him. He is Dr. M. Katachalam. He is from Department of Mathematics, Combinatorics Arts and Science. His area of specialization is graph theory. He has got PhD in mathematics, graph theory from Anna University, Chennai in 2013 with the title A Study on Becoloring of Graph with a Metric Relationship to Achromatic, Star, Equitable, and Harmonious Coloring. Today, he brings a presentation entitled The B-Chromatic Number of Corona Graphs. Well, Mr. Dr. M. Katachalam, are you ready for having presentation?
Yes.
Okay, all right. So time is yours.
Okay. So Very good morning to one and all gathered here. First of all, I thank Professor Defik and his group, second research group, for inviting me again in the 2020 for delivering a talk on graph coloring. I thank our management, secretary and director, Dr. C.A. Basuki, Kongunadu Arts and Science College, Coimbatore, Tamil Nadu, India. I thank our principal, Dr. M. Lakshmana Swami, Kongunadu Arts and Science College, Coimbatore, Tamil Nadu, India. I thank Dr. V. Kogilavani, Head of the Department of Mathematics, Kongunadu Arts and Science College, and my colleagues, Dr. Vigneswaran, Dr. Vijayalakshmi, Dr. Mohan Priya, Dr. Ravichandran, and other friends. Now, today I am going to talk on the title, The B Coloring of Corona Graphs. Shall I share my screen?
Pardon me, sir?
Shall I share my screen? I am unable to share my screen.
Yes, brother. Please share your screen.
Able to do it. Only the host can share this meeting.
Anis, please eligible him to be a co-host.
Okay. Can you see my PPT?
Not yet, sir. Yes.
My PPT is visible now?
Okay, we can see your PPT.
Okay. So my entire title of my talk is The B Coloring of Corona Graphs. First, I start the formal definition of graph. A simple graph G with n vertices and m edges consists of a vertex set V of G, V1, V2, etc. Vn, and the edge set E of G, E1, E2, etc. En, where each edge is an unordered pair of vertices. We write UV for the edge U, V. If UV belongs to E of G, then U and V are adjacent. The vertices contained in an edge E are its endpoints. So this is example F. Here we have 7 vertices and 8 edges. So in our talk today, I have considered only the simple graph. Simple graph means without loop and parallel edges. And as far as I have considered only the connected simple graph. So connected graphs, any pair of vertices must have a path. And disconnected means the any pair of vertices there is a no path means it is disconnected graph. Now definition for a proper vectors coloring. So the coloring means assign the coloring to the vertices. So coloring means itself vertex coloring. We can assign the color for the edges. That means edge coloring. Or we can assign the colors to the both vertices and edges. It is called total coloring. Here I have considered the vertex coloring. They are simply coloring. So the coloring means we have some constraint. The first condition is the assignment of colors to the vertices of a graph so that no two adjacent vertices have the same color. So this is the first constraint. And chromatic number. Chromatic number means the condition is we have to consider only the minimum number of colors. That is the least number of colors needed to color the graph is called the chromatic number, denoted by chi. That is chi of G. A graph that can be assigned A proper K coloring is a K colorable and is denoted by and it is K chromatic if its chromatic number is exactly K. If we use the K color, then the minimum, that is the minimum, then the chromatic number is exactly K. So this is the example of the proper wet coloring. Here I have cut the cycle C6, that is cycle with the even number of vertices and the cycle with the odd number of vertices. The first example C6, in a cycle C6 we need only two colors, that is minimum two colors are enough to color the graph by proper coloring. That is, here I have assigned the colors 1 2 1 2 1 2. In the case, in the same cycle, if the odd number of vertices means we need a minimum three colors, that is 1 2 1 2. Here we cannot assign color same 1 and 2, so we must use the color 3 for proper coloring. So in general, for a cycle, the chromatic number of cycle with n vertices, the chromatic number is 2 if n is even. If the chromatic number is 3 if n is odd. The path, we need only two colors. Chromatic number of any graph G equal to 1 if and only if it is totally disconnected. The chromatic number of a graph G greater than or equal to 3 if and only if G has an odd cycle equivalently if G is not bipartite. Chromatic number for complete graph equal to n. Since in a complete graph is adjacent to all other vertices, so we need n different colors for proper coloring. Chromatic number of any tree which is equal to 2 and the chromatic number that is bounds, Brooks theorem. Chromatic number of any graph G is less than or equal to maximum degree delta of G plus 1 unless G is a complete graph or an odd cycle. That is the Brooks theorem. The chromatic number of any graph G less than or equal to 4 for any planar graph G. This is the main, the famous theorem, 4-color theorem. Now I am entering with B coloring. So normally in ordinary chromatic number, the ordinary vertex coloring, we consider only the minimum number of colors. Here in the B coloring, here we are going to consider maximum number of colors. So that is the different constraint. The concept of B chromatic number was introduced in the year 1999 by Irving and Mello, who proved that determining B chromatic number of G, that is pi of G. Here we are using the notation for B chromatic number pi of G is NP hard in general and polynomial for trees. Also they showed that the B chromatic number is bounded by chromatic and the achromatic numbers. That is, chromatic number means we already discussed. The achromatic number means this is also a max number of colors. Number of colors. The achromatic number means it is a proper coloring. We consider only the maximum number of colors, and another constraint is each and every pair of colors must be appeared on at least one edge. If we use 5 colors, for example, 1, 2, 3, 4, 5, all pass pairs 1, 2, 1, 3, 1, 4, 1, 5, 2, 3, 2, 4, 2, 5, 3, 4, 3, 5, and 4, 5 must be appeared on at least one edge. And we must use the maximum number of colors, that is the chromatic number. The B chromatic number is bounded between the chromatic number and achromatic number. The achromatic number notation is chi C of G. So while defining the B coloring, Irving and Manlow, and they showed that it is B chromatic number is bounded by the chromatic and the achromatic number, that is chi of G less than or equal to pi of G less than or equal to achromatic number, that is chi C of G. Where chi C of G, that is achromatic number, is the maximum number of colors such that any pair of colors appears in G. Any pair of colors, all the pairs must be appeared in the G. Now, the definition for B coloring. The B chromatic number pi of G of a graph G is the largest positive integer K such that G admits a proper K coloring in which every color class has a representative adjacent to at least one vertex in each of the other color classes. Such a coloring is called a B coloring. So once again I am explaining the B chromatic number means it must be a proper coloring, and we have to consider the largest positive integer K, and in each, and another main constraint for the B coloring is in which every color class has a representative adjacent to at least one vertex in each of the other color classes. Such a coloring is called a B coloring. For example, if we use 4 colors, that is C1, C2, C3, C4. I am considering C1 as a color class, and the color class for C2, and the color class for C3, and the color class for C4. The color C1 assigned for 5 vertices, and similarly the color C2 assigned for 5 vertices, and C3 assigned for 5 vertices, and C4 assigned for 5 vertices. Just I am collected as a color class C1, color class for C1, C2, C3, C4. In C1, there are 5 colors. The first vertex, the color assigned C1 for only one time. Sorry, the color the first vertex, the assigned color C1, which is not adjacent to any of the vertex of the other color classes color classes of C2, C3, C4, and the second vertex of the color class C1, which is adjacent to a vertex in the color class of C2, that is the color class of C2, the first vertex, the yellow color, and the third vertex of a color class C1, which is adjacent to a vertex from a color class C2, as well as in the adjacent to a vertex of the color class C3, adjacent to the vertex of a color class C4. So in the color class of C1, the third vertex is adjacent to at least one vertex of a color class C2, C3, and C4. Similarly, in the color class of C2, see the fourth yellow color vertex, not fourth one, the first one. The fourth one is adjacent to the color class vertex in the color class C3 and C4, which is not adjacent to a vertex of the color class C1. But the first vertex is adjacent to the color class of C1, color class of C3, and color class of C4. Similarly, in the color class C3, the third vertex, the green color, the third vertex adjacent to a vertex in the color class of C1, C2, and C4. In the color class of C4, the final vertex, which is adjacent to a vertex in the other color classes C3, C2, C1. So it is clear that the bichromatic, the condition is every color class has a representative vertex which is adjacent to at least one vertex in each of the other color classes. Such a coloring is a B coloring. We have to consider only the maximum number of colors to satisfy these conditions, proper coloring and the B coloring conditions. The upper bound for the B chromatic number, here we upper bound B chromatic number, the B chromatic pi G, which is less than or equal to maximum degree plus 1. Okay. So today I am going to discuss about the B coloring of corona graphs. Here in the corona graphs, I am considering the number of vertices in the G corona H and the number of vertices in G and H are same. We investigate the bichromatic number of the corona product of two graphs of the same order. Okay, same order means the number of vertices, the both G and H have the same number of vertices. So the corona of two graphs, G1 and G2 is the graph G equal to G1 corona G2. So formed from one copy of G1 and mod V of G1 copies of G2, where the ith vertex of G1 is adjacent to every vertex in the ith copy of G2. For example, here I am consider the G is a C for cycle with the 4 vertices and H is a path with the 2 vertices. The G corona H, here in the C4 we have 4 vertices, so we must take the 4 copies of H and 4 copies of H, and each H is adjacent to every vertex of G. Thus, this is the example for G corona H. So this is the another example corona of C5 under the path P2. In the C5 we have 5 vertices. So we must take the 5 copies of P2, and each P2 is adjacent to every vertex of a C5 cycle with the 5 vertices. Now I am going to discuss about the bichromatic number on corona of any graph with path. G may be any graph and H is a path. Okay, and I am considering the G be a simple graph on n vertices. The H also a path with n vertices. Here the number of vertices for G and P are same. The result is the bichromatic number of G corona Pn, which is equal to n plus 1 for n less than or equal to 3, which is equal to n for n greater than 3. So the proof, let V of G equal to V1, V2, V3, etc. Vn, and V of Pn, that is vertex set of G is V1, V2, etc. Vn, and vertex set of path Pn is U1, U2, etc. Un, and the vertex set of G corona Pn, we must take n copies of Pn. So the vertex set of G corona Pn is, that is Pi1 equal to I is not equal to n, and the union of I is 1 to n, j varies from 1 to n. By the definition of corona graph, each vertex of G is adjacent to every vertex of a copy of Pn. That is, every vertex Vi of V of G is adjacent to every vertex from the set Uij. The j is varies from 1 to n. Now we have considered the vertex. We have assigned the. We have considered the vertex set of G, vertex set of Pn, and vertex set of G corona Pn. Our aim is to assign the B coloring for vertex set of G corona Pn as follows. Now I am assigning the is G then color Ci to Vi. Assign the color Ci to Vi. That means assign the color C1 to V1, C2 to V2, C3 to V3, C4 to V3, etc. Cn to Vn. For 1 less than or equal to I less than or equal to n, assign the color Ci to U1i. That is, as per the definition of the corona graph, we are considering the n copies of Pn. The first copy we are labeled for the vertices, that is U I comma j, that is U1 comma I, and for the second copy U2 comma I, the third copy U3 comma 3I, fourth copy U4I, etc. The nth copy UNI. The I varies from 1 to n. Here assign the color C1 to, here I is for every I not equal to 1. So we start with C2, assign the color C2 to U12, C3 to U13, etc. Cn to U1n. We are not assigning the color for U11. We will see it later. And for 1 less than or equal to I less than or equal to n, assign the color Ci to U2i for every I not equal to 2. That means assign the color C1 to U21 and I not equal to 2 here. So for U22 we didn't assign the color. So C3 to U2, C4 to U24, etc. Cn to U2n. For 1 less than or equal to I less than or equal to n, assign the color Ci to U3i. Here for every I not equal to 3. So that means C1 to U31, C2 to U32, and here U33 we didn't assign the color. So C4 to U34, etc. Cn to U34. For 1 less than or equal to I less than or equal to N, assign the color Ci to U4I for every I not equal to 4. That means C1 to U41, C2 to U42, C3 to U43, and for U44 we didn't assign the color, C5 to U45, etc. Cn to U4n, etc. etc. For 1 less than, similarly we assign the color for another copies U4, 5i, U6i, etc. And for 1 less than or equal to I less than or equal to n, assign the color Ci to Uni, and for every I not equal to n, that is C1 to UN1, C2 to UN2, C3 to UN3, etc. Cn minus 1 to UN n minus 1. Here UNN we didn't assign the color. Here only the balanced number of vertices U11, U22, U33, U44, and in the nth copy UNN we are not assigned the color so far. For 1 less than or equal to I less than or equal to n, assigned to the color UII, that is U11, U22, U33, U44. One of the allowed colors, such color exists. Already we used the colors 1 to n. We can, by the condition of the proper coloring, we can use the one of the allowed colors already exist. Since we can assign the color for UII easily, since the degree of UII is 2 or 3. The result is hold for only n greater than 3. Okay. Now, let us assume that, so as per this assignment of our color, the result, actually the result is n plus 1. The result may be greater than or equal to n plus 1. Okay. So now I am going to prove that the result is only the less than or equal to n plus 1. That greater than n, that is plus 1, greater than n, that is n plus 1. That is our result is n. We used only the, in the G corona Pn we use colors C1, C2, etc. n. So only n colors. So as per the definition of B coloring, we have to consider only the maximum number of colors. If we consider one more color extra, that is n plus 1, that is B chromatic number G corona Pn is greater than n. Let us see what will be happened. The B chromatic number of G corona is n greater than or equal to 3. There must be at least n plus 1 vertices of Dn. So again I am going to see here. If we assign the 4 colors, at least 4 vertices must have degree 3. Only then we can have the adjacent to other color classes. Here we are using the 4 colors C1, C2, C3, C4. In the color class C1, the third vertex having the degree 3, and then the color class C2, the first vertex is having the degree 3. In the third color class of C3, the third vertex having the degree 3. Also color class of C4, the final vertex having the degree 3. In general, if you use n colors, at least n number of vertices must have degree n minus 1. Here, in our proof, if we use n plus 1 colors for B chromatic number of G corona Pn, there must be at least n plus 1 vertices of degree n in G corona Pn. Also, another condition is all with distinct colors. Only then we can adopt the condition for the B coloring. And each adjacent to vertices of all other colors, but these be the vertices of G, that is V1, V2, etc. Vn. Since these are only ones with the degree at least n, only the vertices of the graph G in the G corona Pn having degree at least n, but we need n plus 1 vertices, but here we have only the n number of vertices. So this is the contradiction. We are unable to color for G corona Pn with the n plus 1 colors. So the n plus 1 colors is impossible. Thus, we have the bichromatic number for G corona Pn is less than or equal to n. Hence, bichromatic number of G corona Pn equal to n for every n greater than. What about n equal to 1, n equal to 2, and n equal to 3 means? Here we are, I am giving as a note. Note that G corona P1, that is 2. G corona P1 means in G also, since we are considering the number of vertices for G and Pn is same, G corona P1 means that is G also single dot, that is a single vertex. That is G corona P1 means that is P2. P2 is 2 chromatic. Okay. Similarly, the bichromatic number for G corona P2, that is G is edge, and G corona P2 is 3. It is, we can easily draw the graph and we can find the results for graph G on 2 vertices. Indeed, let us notice that such graph G corona P2 includes K3. So K is 3 chromatic. Now let us define B of G corona P3. Okay, so then here the number of vertices of G also 3 with the 4 colors in the following way. For 1 less than or equal to 3, assign the color Ci to Vi, that is 1 to V1, C2 to V2, C3 to V3. For 1 less than or equal to L less than or equal to 3, assign the color Cl to U1L, that is here for L not equal to 1. For 1 less than or equal to L less than or equal to 3, assign the color L to U2L, here L not equal to 2. Similarly, 1 less than or equal to L less than or equal to 3, assign the color Cu U3L, here L not equal to 3. And for 1 less than or equal to L less than or equal to 3, assign the color C4 to ULL, that is assign the color C4 to U11, U12, U22, U33. Therefore, bichromatic number of G corona P3 is greater than or equal to 4. Let us assume that bichromatic number of G corona P3 is greater than 4. That is bichromatic number G corona P3 equal to 5. There must be at least 5 vertices of degree 4 in G corona P3, all with distinct colors, and each adjacent 2 vertices of all of the other colors. But then these must be the vertices V1, V2, V3, only the 3 vertices having at degree at least 4. Therefore, we cannot assign 5 colors. This is the contradiction. So B coloring with 5 colors is impossible. Thus, we have bichromatic number G corona P3 is less than or equal to 4. Therefore, bichromatic number of G corona P3 equal to 4. Hence, bichromatic number of G corona Pn, which is equal to n plus 1 for every n less than or equal to 3. The same bichromatic number for G corona Pn equal to n for every n greater than 3. If n less than or equal to 3 means the result is n plus 1. Here the example. Here G corona P3. So as per our proof, Ci to Vi, C1 the color 2 is for V2, the color 3 is for V3, and each and every copies. And here we are using the colors, other colors. For the first copy, for a vertex of V1 of a graph G, we are using the color 1. The remaining colors 2, 3, 4 assigned in the P3. And for the second copy, we are assigned the 2 for V2 and assigned the color 1, 4, 3 and assign the color 3 for V3 and assign the remaining colors 1 to 4 for the third copy of H, that is G corona P3. Here, see here one is 2, 1, 4, 1, 2, 4. Here we are using the color 4 colors. The 4 colors are bichromatic. Here we cannot use the 5 colors. Here we cannot use 5 colors, since if we use the 5 colors as bichromatic, at least 5 vertices must have the degree 4. Here only the 3 vertex, that is V1, V2, V3 are having degree at least 4. So we cannot assign color 5. So the result for G corona P3 is only 4. Similarly, the bichromatic number of corona graph of any graph with the cycle, the result is n. Here also, as considering the V of equal to V1, V2, etc. Vn, and V of Cn is U1, U2, etc. Un, and the vertex set of G corona Cn is Vi union Uij, the same concept of Pn. By the definition of corona graph, each vertex of G is adjacent to every vertex of a copy C. Every vertex Vi belongs to V of G is adjacent to every vertex from the set Uij, 1 less than or equal to j less than or equal to n. Here also assign the color n coloring for G corona Cn as bichromatic as follows. For 1 less than or equal to I less than or equal to n, assign the color Ci to Vi, that is C1 to V1, C2 to V2, C2 to V3, and etc. Cn to Vn. For 1 less than or equal to I less than or equal to n, assign the color Ci to U1I. Here also I not equal to 1, that is for U11 we are not assigning the color for U11, and for 1 less than or equal to I less than or equal to n, assign the color Ci to U2I, that means C1 to U21, same like the path Pn. Here also for U22 we are not assigning the color. For 1 less than or equal to I less than or equal to n, assign the color Ci to U3I. Here also I not equal to 3. For U33 we are not assigning the color. Similarly, for U44 we are assigning the color, etc. For 1 less than or equal to I less than or equal to n, assign the color Ci to Uni. Here I not equal to n, that means assign the color C1 to UN1, C2 to UN2, etc. Cn-1 to UNn-1. That means for UNN we are not assigning the color. Now we are going to assign the colors for U11, U22, U33, U44, etc. UNN. From one of the allowed colors, such color exists. Since the degree of U11, U22, U33 is 3, so we can easily assign pick the colors from 1 to n, already assigned colors. Therefore, the bichromatic number of G corona Cn, which is greater than or equal to n. Okay, let us assume that bichromatic number for G corona Cn is greater than n. That means bichromatic number of G corona Cn equal to n plus 1 for every n greater than or equal to, n greater than 3. There must be at least n plus 1 vertices of degree n in G corona Cn, all with distinct colors, and each adjacent to vertices of all other classes, all other colors. But these must be the vertices, only the vertices of G, that is V1, V2, etc. Vn. Since these are only ones with degree at least n, therefore we need n plus 1 number of vertices. Here we have only the n number of vertices having at least degree n. So this is the contradiction. We are it is never possible for assigning the B coloring with n plus 1 colors. So B coloring with n plus 1 colors is impossible. Thus we have bichromatic number of G corona Cn is less than or equal to n. Hence bichromatic number of G corona Cn equal to n. Note that bichromatic number of G corona C3 equal to 4. G corona C3 includes K4. Okay, so we must use only 4 colors. Here bichromatic number of corona graph of star graph with the path. That is in the star graph we are taking the notation for K1, n, the one with the Pn. The result is plus 1. Here the vertex at K star graph K1, n, that is V of K1, n equal to V1, V2, etc. Vn plus 1. And the vertex set of Pn equal to U1, U2, etc. Un. By the definition of star graph, V1 is adjacent to Vi, The i's varies from 2 to n. Let vertex set of k 1 comma n, that is star graph corona path, that is k 1 comma n corona pn equal to vi, I varies from 1 to n plus 1, union uij, I varies from 1 to n plus 1, j varies from 1 to n. By the definition of corona graph, each vertex of kn, each vertex of k1 comma n is adjacent to every vertex of a copy pn. Every vertex vi of vertex set of v of g is adjacent to every vertex from the set uij, that is 1 less than or equal to j less than or equal to n. Assign the following plus 1 coloring for k1 comma n corona pn as b chromatic. For 1 less than or equal to I less than or equal to n plus 1, assign the color ci to vi, that is c1 to v1, c2 to v2, etc. c n plus 1 to v n plus 1. For 1 less than or equal to L less than or equal to N, assign the color CL to U 1L for every L not equal to 1. That means here for U1 comma, U11, we are not assigning the color. Similarly, for U2L, here also L is not equal to 2. For U22, we are not assigning the color. So the third copy, L not equal to 3. For U33, we are not assigning the color. For fourth copy, U4L, L not equal to 4. For U4, we are not assigning the color, etc. For 1 less than or equal to L less than or equal to N, assign the color CL to U, NL. Here also L not equal to N. For UNN, we are not assigning the color. For 1 less than or equal to L less than or equal to N, assign the color CL to UN plus 1L. For 1 less than or equal to N less than or equal to N, assign the color Cn plus 1 to ULL, that is Cn plus 1 to U11, same Cn plus 1 to U22, etc. UNN. Therefore, B chromatic number of star graph K 1 comma n corona Pn, which is greater than or equal to n plus 1. Let us assume that B chromatic number of star graph K 1 comma n corona Pn is greater than n plus 1, that is B chromatic number of star k1 comma n corona pn which is equal to n plus 2. There must be at least n plus 2 vertices of degree n plus 1 in k comma n corona p, all with distinct colors and each adjacent vertices of all the other colors. But these must vertices v1, v2, v3, etc. vn comma v, that is n plus 1 number of vertices vi and v. Since these are only ones with degree at least n plus 1, we need n plus n 2 number of vertices. Here we have only the n plus 1 number of vertices having degree at least n plus 1. So the B coloring with the n plus 2 color is impossible. Thus we have B chromatic number of star k1 comma n corona pn which is less than or equal to n plus 1. Hence B chromatic number of k1 comma n corona pn which is equal to n plus 1. Based on the above results, here I am generalization of B chromatic number of corona graph of any two graphs of the same order are going to present. Let G and H are simple graphs, each one on n vertices. The B chromatic number of corona of any two graphs, that is G corona H, which is equal to n. Here the results are based on the maximum degree of the H. If the maximum degree of H is less than n minus 1, the result is n. If the maximum degree of H which is equal to n minus 1, strictly equal to n minus 1, the result is n plus 1. So this is the main result of this talk in this work. That is the B chromatic number of corona of any two graph. But the number of vertices in G and H are the same. Let V of G equal to V1, V2, etc. Vn and V of H equal to U1, U2, etc. Un. Let V of G corona H equal to Vi, where I varies from 1 to n, union Uij, I varies from 1 to n, j varies from 1 to n. By the definition of corona graph, each vertex of G is adjacent to every vertex of a copy of H. That is, every vertex Vi belongs to V of G is adjacent to every vertex from the set Uij, j varies from 1 to n. Let us rename the vertices in ith copy of H in G corona, the I varies from 1 to n in such a way that the vertex of maximum degree has a label UII. That is, in the corona of G corona H, in the all the copies of H, in the first copy for U11, you are assign U11 for a maximum degree vertex. In the second copy, assign U22 for a maximum degree vertex. In the third copy also, assign U33 for a maximum degree vertex, etc. In the nth copy, label the vertex UNN for a maximum degree vertex. For the proof purpose, we are considering without loss of generality. We are considering like this. Assign the following coloring for G corona H as B chromatic. The same idea from G corona PN and G corona CN and star graph with PN. Same idea we are following here. For 1 less than or equal to I less than or equal to N, assign the color CI to VI. Assign C1 to V1, C2 to V2, C3 to V3, sorry, C3 to V3, etc. Cn to Vn. For 1 less than or equal to I less than or equal to N, assign the color Ci to U1I. Here also for every I not equal to 1, that is for U11 we are not assigning the color. Similarly U22 not assigning the color. The third copy assign Ci to U3I for every I not equal to 3. For U33 we are not assigning the color. The fourth copy assign Ci to U4I. Here also we are not assigning the color for U44. In the last copy for I varies from 1 to N, assign the color Ci to UNI. Here also I not equal to N. Here also for UNN we are not assigning the color. For 1 less than or equal to I less than or equal to N, assign to vertex UII, that is U11, U22, U33, etc. UNN. One of the allowed color, such color exists since the degree of UI varies from 1 to N, that is less than N. 1 less than or equal to degree of UII less than N. Therefore, we can easily from the assign the colors to U11, U22, U33, etc. UNN, one of the allowed colors. 1 minute. Therefore, B chromatic number of G corona H, B chromatic number of G corona H greater than N, greater than or equal to N. Let us assume that B chromatic number of G corona H is greater than N. That is, B chromatic number of G corona H equal to N plus 1. There must be at least N plus 1 vertices of degree N in G corona H, all with distinct colors, and each adjacent to vertices of all of the other colors. But these must be the vertices V1, V2, Vn. Since these are only ones with the degree at least N. So this is the contradiction. B coloring with the N plus 1 colors is impossible. Thus, we have B chromatic number of G corona H is less than or equal to N. Hence, B chromatic number of G corona H equal to N if maximum degree H less than N minus 1. In the case 2, if B chromatic number of G corona H, if maximum degree of H equal to N minus 1, the same idea followed for maximum degree of H less than N minus 1 are following here. One thing is for 1 less than or equal to I less than or equal to N, assign the color Cn plus 1 to UII. That is Cn plus 1 to U11, U22, U33. Therefore, B chromatic number of G corona H is greater than or equal to N minus 1. Let us assume that G chromatic number of G corona H is greater than N minus 1. That is, B chromatic number of G corona H equal to N plus 2. There must be at least N plus 2 vertices of degree N plus 1 in G corona H, all with distinct colors and each adjacent vertices of other colors. But these must be vertices V1, V2, V3, Vn. Since these are only ones at least N, this is the correction. So N plus 2 colors are impossible. So the result is N plus 1. Here the example. Here we are considering G corona H, that is P6, that is path with 6 vertices, and H is wheel with 6 vertices. In the wheel graph, only the hub vertex having the maximum degree. So in each and every copy of the wheel graph, in the hub vertices, we are assigning the color n plus 1. That is, here we are using the colors 1 to 7. Here n plus 1 is only 7. So we are assigning the 7 to each and every copies of H for a hub vertex. That is, in the wheel graph, in the hub vertex, in the middle, we are assigning the 7. Only then we can achieve the result is n plus 1. For the graph G is assigned the V1 to V1, the color 2 is V2, color 3 is V3, color 4 for V4, color 5 for V5, and color 6 for V6. I think the time over. So the B coloring result discussed can be extended to the same corona of any two graph. Here I found the result for G corona H. The number of vertices of G and H are same. If number of vertices are different, what is the B chromatic number? This is the open problem to all. And the same result, the B coloring discussed here can be extended to the subdivision vertex corona, edge corona, and other types of corona of two graphs. These are all the open problems. The same problem can be extended to find the middle total central graphs of a graph. These are all the open problems. And these are all the references. There are good number of papers published in reputed journals, Scopus and CA Index journals, Discrete Applied Mathematics, Utilitas, and other journals. I am happy. These are all my 3 papers on B coloring. The first paper in the Springer journal, and the second one is Utilitas Mathematica, and the third one is Lee Mathematici. And for lecture review, one paper, the B chromatic number and related topics, a survey paper published in Discrete Applied Mathematics. In this paper, they are considered all the published B chromatic numbers and discussed here the survey paper. If you read this paper, you get the idea of already published results. Then you can move to further work. These are all the publications. Here, the results which is myself and Reginald Vivin, Mathematic Chronograph. The work is published in Utilitas Mathematica in the year 2012. Now I conclude my talk. Any questions?
Well, okay. Thank you, Dr. Fan. Well, ladies and gentlemen, so we will go to questions and answer session. Please, you may deliver questions to Dr. Fan, talking about the B chromatic number of corona graphs. You may directly unmute your microphone and then Dr. Fan, or you may type your questions through chat box. Go ahead.
Good morning. May I ask a question?
Yes, go ahead. So you want to ask to Dr. Fan?
Good morning, Professor.
You can ask.
Yeah, my question is very...
Yes, madam.
Hi. I have a very simple question. What is the significance of B? What is B in the B chromatic number? Is that for balance? Did you get
Actually, the author defined in the B coloring concept. The giving the title that is B
Yes.
coloring. That
Yes.
is the B coloring means that is the, I think this is the balanced coloring. Since in each and every color class, at least one representative vertex must be adjacent to a vertex in the other color classes.
Okay.
So that there is the relationship between all other color classes.
All right. So
Even though the proper
B,
coloring, here we are using the maximum number of colors.
uh-huh. So B stands for balanced.
Yeah.
Okay, thank you.
Thank you.
Well, thank you for Mrs. Garciano Agnes from Philippines. Please, other participants, we have still time to have questions and answers. Well, okay. Excuse me, Dr. Fan. Can you hear my voice?
Yeah.
Well, okay. So there is a questions through the chat box. So let me read for you.
Okay.
What is the concept of your research in regards to the real world? What is the application? Can you get it?
Yeah.
Okay.
Actually, I worked in the pure mathematics. That is, I find the results in the pure graph coloring. That is the p chromatic number of various graphs. And in the real life, I didn't work for any results for the real life application of B coloring. But there in the literature, there are some real life applications of B coloring. We can find it here. And ordinary chromatic number having the some application in the real life problems. That is in the chemical laboratory. We cannot have all the chemicals in the same container, since it may get the fire. And in that situation, the chemicals can be considered as vertices. And if you assign the proper coloring and the minimum number of container, we are enough to accommodate all types of chemicals without the problem in the chemical laboratory. The same chemical laboratory problems may be extended to find the real life application of B coloring. Sorry, I didn't find any real life application of B colorings.
Thank you, Dr. Fan, for answering the questions. Well, okay, so we are still waiting for the other participants who want to ask questions to Dr. Fan. I will repeat his talk about the B chromatic number of corona graphs. So you may ask about that topic. So we are still waiting for the other participants to deliver questions. Dr. Fan?
Yes, sir.
Okay, perhaps all of the participants have understood about your topic. Thanks a lot for presentation, and also thanks a lot for joining this conference, being the invited speaker.
Thank you.
Okay. Before we end this first plenary session, I will call back Professor Adil Baghirov. Are you still there, Professor Adil Baghirov?
Yes, I am here.
Thanks a lot, sir. Well, excuse me, there is one question from Mr. Kamal. He is from Morocco.
Yes.
Let me read the questions for you. The questions is about the classifications. For the case of two convex sets, it is known from the Hahn-Banach spiration theorem that we can spare it to convex sets with a hyperplane.
Yep.
Can we use this result for the more general case of polyhedral classification by partitioning the space into linear subspace and apply the Hahn-Banach theorem for the more general case? That's the question, sir.
Okay, I don't know such result, and I cannot say that no, but I am not sure. So my answer, because Hahn-Banach theorem is purely based on convexity assumption. But here we have two sets which are one is you can consider as a convex, but another one is certainly non-convex. So, but I don't want, how to say, to discourage someone not to dig into detail of that one. Maybe you can find some interesting result coming from Hahn-Banach theorem, but you may get some good results there. That's quite possible.
Okay, thank you for your confirmation.
Sorry, and also please note that here we have sets which are finite point sets. But in convex analysis, we consider sets which are usually not, say, finite point set. Yeah, thank you.
Okay, all right. Thank you for your confirmation, Professor Adil Baghirov. Well, ladies and gentlemen, this is the end of the first plenary session. Thanks a lot for Professor Adil Baghirov, Professor Basuki Widodo, and thank you for Dr. M. Katachalam. Once again, please give a big applause virtually for all of the invited speakers today.
Okay, thank you very much.
Thank you.
Well, ladies and gentlemen, I return this event to the Master of Ceremony. I am Rizky Febri and my partner Rido Alfarizi say thank you very much for your joining and the participation. See you tomorrow in the second plenary session, and goodbye.
Ladies and gentlemen, this is the end of the presentation session. We are going to have a break, but before that, we are going to inform you the rules for the next parallel session. First, participants should use their full name, while presenters should use their paper ID _ full name. For example, 001 _ Rosanita. Second, participants should accept the breakout request from the host by clicking Allow. Third, participants should turn the audio off when it is unnecessary. Fourth, participants should not leave the meeting until the parallel sessions ends. Fifth, the certificate will be given only if the participant joined the Zoom meeting in the first and second day of ICCGANT 2020 plenary session. Sixth, the presenter that hasn't been presenting in the first day will present in the second day of ICCGANT 2020. Seventh, further questions and information, please contact our host by clicking Ask for Help button. Thank you.
Acara selanjutnya adalah ISOMA, namun sebelum itu perlu kami informasikan terkait tata aturan dalam sesi paralel ICCGANT 2020 melalui Zoom Meetings. Di antaranya, yang pertama, Peserta dimohon untuk menulis nama lengkap dan untuk presenter dimohon untuk membubuhkan nomor paper ID di depan nama dengan contoh 001 garis bawah Rosanita. Kemudian yang kedua, peserta dimohon untuk menerima permintaan breakout dari panitia dengan cara mengklik kata allow. Kemudian yang ketiga adalah peserta dimohon untuk menonaktifkan audio ketika tidak digunakan. Keempat, peserta dimohon untuk tidak meninggalkan Zoom meeting hingga acara parallel session berakhir. Yang kelima, sertifikat akan diberikan dengan syarat peserta wajib mengikuti Zoom meeting hari pertama dan kedua ICCGANT plenary session. Kemudian bagi presenter yang belum presentasi pada hari ini dimohon untuk presentasi besok dalam ICCGANT 2020 hari kedua. Apabila ada pertanyaan lebih lanjut dimohon untuk klik tombol Ask for Help dan akan terhubung dengan host kami.
We are going to have 45 minutes breaks. The parallel session will be start at 12:15 Western Indonesia time. You can leave the meeting and signing back in using the same ID and password.
Acara selanjutnya adalah Isoma selama 45 menit dan kita akan melanjutkan parallel session pada pukul 12.30 waktu Indonesia Barat.
Welcome back to the fourth ICCGANT 2020. We are going to have the parallel session, and these are the following rules. First, participants should use their full name, while presenter use paper ID underscores full name. For example, 001 underscores Rosanita. Second, participants should accept the breakout request from the host by clicking allow. Third, participants should turn the audio off when it is unnecessary. Fourth, participants should not leave the meeting until the end of the parallel sessions. Fifth, certificate will be given only if the participant joined the Zoom meeting in the first and second day of ICCGANT 2020 plenary session. Sixth, the presenter that hasn't been presenting in the first day will present in the second day of ICCGANT 2020. Seventh, further questions and information, please contact our host by clicking Ask for Help button. And also, we would like to remind that ICCGANT 4th 2020 will be continued tomorrow at 8 Western Indonesia time.
Acara selanjutnya adalah parallel session. Namun sebelum itu perlu kami informasikan kembali terkait tata aturan dalam sesi paralel ICCGANT 2020 melalui Zoom meetings. Di antaranya, yang pertama, peserta dimohon untuk menulis nama lengkap, dan untuk presenter dimohon untuk membubuhkan nomor paper ID di depan nama dengan contoh 001 garis bawah Rosanita. Yang kedua, peserta dimohon untuk menerima permintaan breakout dari panitia dengan cara mengklik kata allow. 3. Peserta dimohon untuk menonaktifkan audio ketika tidak digunakan. Keempat, peserta dimohon untuk tidak meninggalkan Zoom meeting hingga acara parallel session berakhir. Sertifikat akan diberikan dengan syarat peserta wajib mengikuti Zoom meeting hari pertama dan kedua ICCGANT plenary session. Bagi presenter yang belum presentasi pada hari ini, dimohon untuk presentasi besok dalam ICCGANT 2020 hari kedua. Apabila ada pertanyaan lebih lanjut, dimohon untuk klik tombol Ask for Help dan akan terhubung dengan host kami. ICCGANT 2020 hari kedua akan diselenggarakan besok pukul 8 waktu Indonesia Barat, dan penutupan acara hari ini akan ditutup di setiap room masing-masing. Terima kasih.
you.